Good afternoon, distinguished colleagues and guests. It's April 20th, 2021, 2 p.m. Moscow time. We're beginning the panel session for the defense of the thesis by Ivan Zaitsev. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 010303, solar physics. The topic of the thesis is acceleration mechanism of thermal ions during magnetic reconnection. Under the order issued by the academic secretary of St. Petersburg State University as of February 9th, I, Viktor Sergeyev, Doctor of Sciences in Physics and Mathematics and Professor of Earth Physics, Department of St. Petersburg State University, was appointed the chairperson of the Dissertation Board. The order also approved the candidacies of the members of the board, and let me introduce them. Nadezhda Zolotova, Doctor of Sciences in Physics and Mathematics, Associate Professor of the Earth Physics Department of St. Petersburg State University, and the following members of the board are working in remote mode. Vladimir Troyan, Doctor of Science, Professor of the Physics Department of St. Petersburg State University, ECS and SOK. Yelena Grigorenko, Doctor of Sciences in Physics and leading researcher of the Space Research Institute of the Russian Academy of Sciences. Yelena, do you hear us and see us? Yes, yes, I do. Okay. Eldar Shahislamov, Doctor of Sciences in Physics and Mathematics, Deputy Director for Academic Affairs of the Institute of Laser Physics of the Siberian branch of the Russian Academy of Sciences. Do you see us and hear us? Yes. And Andrei Samsonov, Doctor of Sciences in Physics and Mathematics, researcher at the University College London, the United Kingdom. Do you see us and hear us? Yes? Yes, I do. Everything's okay? Okay. Great. And we also have our candidate for the degree, Ivan Zaitsev. We also have the thesis supervisor, Andrei Divin, candidate of Sciences in Physics and Mathematics, senior researcher at the Earth Physics Department of St. Petersburg State University. Dear colleagues who are working in the remote mode, in order to improve the quality of our connection, kindly turn off your microphones, but don't forget to turn them on when I give you the floor. I would also like to inform you that the panel session of the Dissertation Board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted into English. Currently we have an email address posted on the page with live broadcast of the board session, and all listeners can submit their questions to Mr. Zaitsev online, and the questions regarding the thesis or scientific discussion. These questions will be forwarded to me by our technical service, and I will read them out during the discussion. Questions must be related to the presentation and the content of the thesis, and don't forget to give your name and position if you submit a question. Questions that have nothing to do with a scientific discussion or dissertation and to the assessment of the dissertation will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts of St. Petersburg State University, the session of the Dissertation Board is valid, providing 2/3 of the appointed board members are present. The total number is not to be fewer than 4 people. The Dissertation Board consists of 6 people. Everyone is with us today, including 4 members of the board who are working remotely. We have multimedia connection with all the members of the board. We have our candidate for the degree here. So we have the quorum, and we can start. Our session is not to be longer than 2 hours, and the agenda is as follows. So it's quite a lengthy list. I'll quickly read it out. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. Then candidate's presentation providing an overview and findings of the research. 15 minutes for that. Then questions to the candidate regarding the presentation. No more than 2 minutes per question. Then candidate's replies to the questions. 5 minutes for all the questions. Then reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions. Every board member will have 10 minutes. Then the chairman's report on the thesis. Then the candidate's comments about the reports on the thesis and replies to questions. 20 minutes for that. Then we're going to have an open discussion. Anyone present at the defense may state their position or ask questions on the thesis. 2 minutes per speaker. And I kindly ask you to fill in the registration form and introduce yourself before I give you the floor. Then the chairman will ask the questions submitted during the broadcast by our website. The candidates replies to the questions, 2 minutes per question. Then the presentation of the candidate's thesis supervisor, 3 minutes for that. And then, if needed, we may organize a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. And this discussion is not broadcast. We can have it or maybe not, depending on the situation. Then we're going to have an open balloting, vote counting, and recording of the results into the protocol. And then we're going to make a decision on whether to confer the academic degree or not. And finally, we're going to listen to the candidate's closing speech, no more than 2 minutes. And that's basically it. So, distinguished colleagues, any questions or objections on this agenda? Okay, if there are no questions, let us proceed. But before that, I kindly ask you to switch off the sound on your mobile phones. Thank you. So, let us start. So, the thesis by Ivan Zaitsev for the academic degree of the candidate of sciences in physics and mathematics and the specialization 010303 solar physics is titled Acceleration Mechanisms of Thermal Ions During Magnetic Reconnection. The thesis was approved for the defense by the order of the academic secretary on January 28, 2021. Ivan Zaitsev has prepared his dissertation at St. Petersburg State University, and Andrei Divin, candidate of sciences in physics and mathematics, senior researcher of the Earth's Physics Department of St. Petersburg State University, is the thesis supervisor. 2 published works describe the research findings of the thesis. Both were published in publications indexed in Web of Science and Scopus. The candidate has submitted the full set of documents to the academic secretary, and the above-mentioned documents comply with item 12 of section 3 of the order on the procedure of granting academic degrees at St. Petersburg State University, and the curator for the defense member of the dissertation board support has all the copies. And before I give the floor to our candidate for the degree, I would like to ask the members of the board if there are any general questions to the candidate for the degree, and is there a need to consider the whole list of documents submitted for the defense? Do we have such a need? Okay, no need for that. Okay. Okay, well then. Let's listen to our candidate for the degree. Ivan, please, you have the floor. Thank you. This work is dedicated to the study of mechanisms of ion acceleration in the process of magnetic reconnection. Magnetic reconnection is a universal process of the conversion of magnetic energy into kinetic and thermal energy of particles. Reconnection may happen near solar area and in the magnetosphere of Earth. Solar bursts and aurora are based on this phenomenon. This reconnection is initiated in the current flow. This leads to the formation of X lines where the magnetic field equals 0. And at that, magnetic power lines, streamlines, are reconnected in these dissipation areas where we see the distortion of freezing in conditions, and then they are distorted under magnetic stress. And ions and electrons demagnetize near the X line on the scale comparable to their inertia skin depth. And this leads to a multi-diffusion area. The emergence of this area with unnatural diffusion is equivalent to the emergence of electric field that works on the current, and the particles being demagnetized near X line gain velocity in this field, and later on, getting to the sphere with a normal magnetic field, they reverse, forming an accelerated flow that bends the initial current flow. Non-stationary borders between the initial current layer and accelerated flow is the front of depolarization, and this process is supported by the continuous magnetic flow going through the normal. And the borders between the connected and non-connected lines are these magnetic separatrices. So the purpose was to define the mechanisms of ion acceleration and heating on reconnection separatrices and within the field reversal region inside the reconnected outflow based on the numerical simulation in the kinetic approximation. So after the short description of the method of study, we are going to consider the results of modeling that imitate reconnection in magnetotail. And it was widely studied by other works, and these results will be compared with the results of modeling that include cold ion population. And in conclusion, we're going to consider one-dimensional kinetic model of bifurcation of the stream sheet of the current sheet. So the modeling was performed based on supercomputers of Lomonosov and Curie using parallel code IPIC 3D, which was used to provide an implicit scheme for macroparticles. The method of macroparticles is that the model space is divided into a mesh for cells, and we calculate electric and magnetic fields, resolving Maxwell Vlasov equation. And here we see the zero function of distribution. And the peculiarity of this method is that the distribution function is not defined directly by the solution of Vlasov equation, and instead of that, we use the motion equations, and the calculated particles number can be reduced significantly due to the preservation of this relation of charge to mass. And initial conditions are defined by the equilibrium configuration with a current sheet of Harris type. And for a Harris type current sheet, it is characteristic that the pressure inside this layer, inside this sheet, equals magnetic pressure on the external area. And in modeling, we also use homogeneous background component, particles of background and current are contained in different masses, and this allows us to track their evolution. This reconnection is initiated by adding small component of the magnetic field to the center of the current sheet, and all the results are given in Alban normalization. The lengths are measured in ion lengths, and Alban velocity is calculated according to the equation given on the slide. For all stimulations, we use the correlation of temperatures of electrons to ions 1 to 5 for particles inside the Harris sheet, and the similar relation is used for temperatures for hot simulation, whereas for cold simulation, the temperature of ions was reduced by a factor of 100. The most important characteristic of a reconnection process is the velocity, which is defined as velocity of change of the magnetic flow between in the X line and the front, concluded between the X line and the front, that equals the electric field in the X point. Temporal evolution of velocity of reconnection is given here on the graph. Initially, we see the phase of slow growth, which is replaced by an explosive phase, and after that, the process becomes quasi-stationary with NB that equals 0.1, and all the mentioned results comply with a quasi-stationary phase. And near X line, less inert electrons accelerate by the field of reconnection, which leads to the formation of perpendicular component of the electronic stream, which is supported by longitudinal electronic jets on separatrices. And the character of motion of electrons and ions is significantly different. And here on the graph, you see in red the current flows for ions, and the blue ones define electrons. And you also see the demagnetization of electrons areas. The difference in scale in demagnetization can be considered using diffuse areas because they are localized in space. In non-collision plasma, the particles can be demagnetized under thermal effects or as a result of the influence of inertia, which is explained by the motion equation for particles. And here we see that demagnetization for ions happens in a wider area than for electrons, and deviation of V to B, that's the black line in this connection area of MZ. It corresponds to the width of this area inside which the balance of power is maintained due to divergence of tensor of ionic pressure. And as for electron diffusion area, it has both internal and external part. In the internal part, this field is supported by non-diagonal components of the tensor of electronic pressure, and in the external we have the gap of convective field, which is compensated by electric inertia, and electrons transfer their energy to ions here. The difference in scale of demagnetization leads to strong electric fields in Y component on separatrices. And here we see the trajectory of ions and electrons traced from one point in the stationary configuration of electromagnetic fields taken from the simulation. And we see that an electron has all these reflections in the inflow area, which leads to the formation of a typical extended function of distribution, and then passing through the proximity of X point, it gets to the accelerated flow, and ion goes directly to the accelerated flow, which leads to the formation of the regime with interpenetrating beams. And after we consider the major peculiarities of reconnection in kinetics, we switch to their modification in case with cold ions. Cold ions, from the point of view of theory, are quite useful because they provide us with an opportunity to have a look at the physics that was previously hidden behind this thermal motion. And at that, this additional study was motivated by the current observations on MMS and cluster satellites. The most important result of modeling with cold ions is that compared with the similar simulations that included hot population, the reconnection velocity grows 1.5 times, although previously we believed that 0.1 was a global invariable. And at that, to the left, you see the results for cold simulation, to the right for hot simulation. And we see that the difference of potentials between this inflow and outflow areas is not changing. And linear sizes of electron diffusion area drop in the cold simulation, and we see the distribution of temperatures, final distribution of temperatures in case with hot simulation is significantly different from the cold ones, though the temperature delta in both models remains the same. The difference in the scale of demagnetization of ions is shown for the vertical profile that penetrates through the X point, and here we see that demagnetization of ions in hot case happens on the linear scale near the gyro radius, and for cold ions the scale of demagnetization is defined by ion inertia skin depth, and that's an important result because previously we thought that they can remain magnetized at smaller scale. From diffusion area we can shift to separate traces, and here we consider two profiles, one before the front and the second one after the front, because this reconnection field is spread only up until the front, whereas the impulse may outreach further together with Alvan wave. And here we see that hot ions are demagnetized in the broad area. And on the following graphs, you see the electric field Y, and here you see this computational velocity, V2B. That's electric field. For hot simulation, we see that the electric field is compensated due to divergence of tensor of pressure before and after the front, whereas in cold ions, these particles are magnetized before the front, and they are effectively accelerated on separate traces before it, which is shown by local peaks in the ion inertia. And just to add up the visual component, the acceleration of separate traces can be seen if we restore the distribution function for the vertical component of velocity along the vertical profile. And here, in case with cold particles, we see that they are accelerated with a beam up until the velocity that is defined by a certain effective velocity, defined by a difference in potentials on separate traces. No beams in hot simulations. We just see smooth growth of velocity of the output, Vx, and mass acceleration of ions on separate traces along the vertical lines in cold simulation. We don't see it in hot simulation, and we also see that parallel temperature dominates in hot simulation in a broad area of space, whereas in the cold ion model we see a narrow band with transverse anisotropy. And we offer a simple model for acceleration of ions on separate traces, which includes homogeneous magnetic field and weak field of reconnection, and the strong field of Hall nature. You see them in equation. And using the motion equation, we see that the velocity of the vertical component depends on the value of polarization drift, electric drift, and initial thermal speed. And in order to describe the dynamic of ions in detail, we carried out test simulations in which we approximated the peak of Hall field with a Gaussian, fixing the difference of potentials at separate tracks and changing the width of the accelerating plot. And we observe three different scenarios. The first one, if accelerating sheet is quite broad, then we see that no distortion of drift energy, and there's no accumulation of energy. If this width is smaller than the inertia gap, then a cold particle will gain energy, whereas for hot particles, the hot particles can lose energy. And we see it on dependency graphs. Here we see the energy gain and width of potential well on the axis. Here is cold population, here is the hot population, and we see that as soon as the width of accelerating plot becomes less than inertia length, we see the acceleration of the beam here, and hot ions are scattered in energies according to energy characteristics. And if we get back to the distribution of anisotropy in 2-dimension, we will see that in broad area inside this accelerated space, we see the dominance of parallel anisotropy. It is demonstrated in blue. It's shown in blue. And at that, it's important that in the area with increased parallel temperature, the velocity of output drops, of outflow drops, and this is demonstrated by the drop of Alvan velocity. And in order to detect the mechanism of a generation of parallel anisotropy, we held a simulation in one-dimensional approximation that describes the connection in the magnetic sheet in heliosphere. So that's what we do. We add up the normal component of the field, of the B field, and we also added up the consideration of the leading field because it's quite characteristic for solar wind. And we observe all the characteristics of connection, the drop of BZ component, the acceleration of velocity, outflow, and we see areas with strong parallel anisotropy that coincide with area that has beams of accelerated ions. And in order to detect the mechanism of generation of such beams, we carried out a range of test simulations. First of all, we should mention that the mechanism of generation of longitudinal acceleration was offered by Cowley many years ago, and in area of reversal of the electronic field in the presence of weak homogeneous electric field, the particle that goes through two or more radiuses, and it will gain two velocities of electric drift. Then it changes direction from perpendicular to parallel one. And at that, this mechanism can be used for a cold particle that flows out of the magnetic field. If we consider a hot population, we'll see passing through particles that will gain these two Alvan velocities. And we'll see also trapped particles that can stay within this accelerated flow for a long time. And here in the graph you see the distribution of the growth of velocity from pitch angle, and you see in red the trapped captured particles, and the black color gives us the flight particles. And you see that some of the particles will stay within this layer for a longer period of time, whereas small pitch angle particles will be efficiently accelerated by a mechanism of Cowley type. And if we add up bipolar variation that corresponds to Hall field, we'll see that they have additional capturing effect, and the particle will have these fluctuations for a long period of time within this accelerated flow. So finally, we have two mechanisms of acceleration. The first one is acceleration at the separatrices of low-energy ions that form perpendicular beams. And second is field reversal region in the exhaust core that traps 90-degree particles and accelerates particles with a small pitch angle, which leads to parallel anisotropy domination, and these particles are efficiently captured within the area of accelerated flow. And here are the provisions taken for the defense. It is shown that cold ions experience effective acceleration when passing through the potential barrier at reconnection separatrices, forming an accelerated beam perpendicular to the magnetic field, while hot ions undergo energy scattering. And in reconnection rate increases the simulation with low energy background ion population, and also field reversal region with the reconnection exhaust generates field aligned ion beams, which is the source of large scale parallel temperature anisotropy. And here is the list of publications. Okay, thank you so much. And now it's time to ask questions. Please, the questions to our speaker. Yes, please. Hello. Ivan, not to mention that later, I'll read one of the comments from my review. I wanted to ask what happens in the internal electron diffusion area. So you showed that the electric field of reconnection is balanced by a non-geotropic part of divergence, and this area takes 1/5 of the ion length, and there was this blue curve that was responsible for the pressure. Yes, so it has certain asymmetry peak, or it changes its value around 0. Could you explain this conclusion? What happens in this area? In this area, electrons accelerate under the influence of electric field of reconnection. Then they get to the area with a low normal field, with small normal field, and then they bend. The velocity from Z component becomes X component. So that's the area in which electrons accelerate and bend. So, yes, it became clear. Thank you. Any other questions, colleagues? Okay, then let me ask. So, an important role is given to this area of separatrix, and you've demonstrated that intensive electric field in the area of separatrix is transferred to the area much quicker than the depolarization fronts goes away. So it transfers this first information about that. So the question is, what are the distances at which this electric field is relaxing? So this energy should somehow be spent. It can't just go away into a kinetic Alvan wave up until eternity. So what can you say about this limitation for EY component? Because EY goes along with this Alvan wave that corresponds to the thermal speed of electrons, and this is a dissipative wave. Therefore, in time, this layer is becoming wider, and it's clear that it can't exist as such from hundreds of RE to internal magnetosphere. However, these waves are observed and they can be transferred to rather long distances. And for Earth magnetosphere, that's dozens of RE. So tons of RE. So that's a rather strict forecast that you can check. Okay, thank you. Any other questions? I have a connected question. What is the numerical dissipation in this diffusion? If you have this diffusion in the scheme. Well, we don't set it ourselves, unlike in other types of modeling. Yet we can calculate diffusion as a relation of electric current to electric field. And as a result, we'll see that this value drops behind the front, and it starts growing at the X point. Maybe it's not relevant to numerical dissipation because your model has demagnetization as well. Did I formulate it correctly? So as far as I understood, you're asking whether we have calculated dissipation if, for example, we use the Ohm law. No, for example, if you If you add up dissipation component, and you can change its value to understand what kind of numerical dissipation we have. Yes, we didn't do it in our work because we've calculated just dissipation as an emergence of anomaly conductivity, and we can calculate it from the Ohm law. We can calculate sigma. So do you associate it with a scheme or with certain processes? We considered its change in neutral plane and in the proximity of diffusion area, how it changes. So we believe that conductivity, the drop of conductivity is connected with reconnection. In the accelerated flow area, it should be much less than in the initial current flow. And we really observe this drop. And it happens for several factors. Okay. Are you satisfied with the answer? Yes, that's a complicated question. Okay. The one that was not studied in detail here. Okay, other questions? Yes, may I ask one? As far as I understand, you use this two-dimensional space, a two-dimensional problem for space, then one-dimensional problem. And what will happen if you consider three-dimensional problem? How do you think, what will change there? Maybe conclusions will change or what? Well, we should understand that this problem is two-dimensional in space, and we calculate all the three values of vector components. It is three-dimensional for velocity, for example. And at that, the width of the cell is defining the dimensionality in this third dimension. So that's the 3D problem with the width of one cell. And if we use a 3D problem, we will observe a range of effects. However, basically, we will, if we multiply this image in third dimension, it won't be that different from the one that we get in 3D modeling. Okay. Okay, are you satisfied with the answer? Yes? So, colleagues, anyone? Maybe you want to ask a question? Well, I want to ask one from my review if we're talking about modeling. Your simulation is not self-coordinated, self-congruent. Well, that depends on the model. A particle model is not self-congruent. It's clear that it's hard to provide self-congruent simulation, but if you've taken the reverse influence on magnetic conservation on behalf of particles, would it influence your test modeling results? How do you think? Certainly. These non-stationary effects can influence the general picture, but those structures that we've considered, they exist in self-congruent modeling at temporal scales of many ion gyro periods. Therefore, we believe that this approximation is applicable. So the separatrices areas and field reversal areas, they are long-living structures. Therefore, we can consider them as quasi-stationary. Okay, that's clear. Thank you. Okay, we've asked questions. I see no other questions. Okay, then, thank you. And now we're going to listen to the reviews of the members of the board with their assessment of the study. And the question is it more certainly will have certain comments, and I offer you to answer the questions after each review, if you don't mind. So no objections about that? Okay. We didn't get any external reviews, therefore we'll shift to our members' reviews. And we start with Nadezhda Zolotova. So please, Nadezhda. Thank you so much. I'll just give a free retelling of my review. First of all, I would like to mention the importance of this work, and as I'm working with solar physics, I'll start with that. As Ivan mentioned, this reconnection process is quite a universal one, and certainly the current sheets and magnetic layers are present on the solar surface, and we see the outbursts of coronary mass that are provided by a reconnection process. How it happens in details is something that is still unclear. And based on Tom Wood's report on one of the recent International Astronomy Society assemblies in 2018, he said that we still can't consider everything in detail, how this outburst process happens, because the temperatures are quite high, therefore light elements are fully ionized, and in the spectra we see nothing from them. We should consider the heavy elements, and they have quite a lot of electrons, a lot of sublayers, and it's hard to choose any of them. Therefore we don't have significant resolution. Either we observe the entire sun with a general resolution, or we observe some certain part in detail. And so we see certain outbursts as just a vague spot. And yet another important problem where this reconnection happens is the heating of corona. And Gold offered this idea of nano flashes. And then Eugene Parker devised an idea of this nano explosions where we have this reconnection process, and as it happens on a smaller scale, the turbulence of kinetic energy that was formed from magnetic one, it dissipates, and the heating process happens. Or maybe the heating happens due to Alvin waves. There are problems there as well, because not everything corresponds with a scale. Therefore, it's hard to understand how this delicate structure of reconnection in exhaust and in separate traces actually look like. And we should say that on the sun's surface, the substance is much hotter, and the problems that Ivan considers, they are mostly dealing with the tail of magnetosphere. But still we see that the reconnection process is quite important, and we need to know the details. Therefore, as for the relevance, it is quite obvious. And I won't dwell upon, I won't repeat what was considered in the thesis. I believe that colleagues will mention that later on. I've already asked the question that I had, therefore I'll mention certain drawbacks. As in many works, the start of the work looks much better. It's well written, though I'm not an expert in the field. Everything was quite okay. I understood everything. And then there were certain insignificant faults. And the quality of images was rather poor. It was hard to see them fully, but these are minor problems. They don't play any role. Therefore, I believe that this is quite a good one. And Mr. Zaitsev deserves the academic degree of the candidate of sciences in physics and mathematics. That's it. Yeah, okay, thank you. Thank you. So he already answered your question. Yes. Yeah, okay, moving forward. Next, Vladimir Troyan. Colleagues, I didn't mention that all the reviews were already published. Therefore, there's no need to read them out. You can stick to them as they're short, but you can also omit some issues that are repeated, and you can just give some basic points, not to repeat everything. Okay, so please, Vladimir. Thank you. Distinguished colleagues, certainly the studying of the structure and dynamics of magnetosphere of Earth is a relevant problem of contemporary physics of order space, and an important role here is placed by magnetic reconnection processes that change the topology of the magnetic streamlines that leads to the transformation of magnetic energy into kinetic and thermal one. For plasma, it should be mentioned that reconnection in the current sheet of magnetotail and on magnetopause, they are the main factors for magnetic storms. And here we also see that the goal of this work, as it was already mentioned, was to define the criteria of efficient acceleration of thermal distribution ions in configurations of electromagnetic fields, characteristic for separatrices of reconnection, and also in the area of the sign change. They also had very interesting numerical experiments of the processes of anti-parallel or reconnection with different initial temperatures of ions, and he studied the dissipation of current sheet. He carried out numerical modeling with particles of the set in the set fields, and this allowed him to shift to basic provisions taken for the defense. And they were defined in the report, and that's why I won't mention them. And for the first time, he carried out the kinetic modeling for anti-symmetric reconnection with low energy ion population. And the study of parameters demonstrated the dependency of the value of ion energy that crosses separatrix from its initial thermal speed. And as for the results of this modeling, they demonstrated that the mechanism of Coulomb that provides for the acceleration of particles when they cross this area of reversal fully works with ions with small pitch angles, whereas particles with large pitch angles, we see them in the exhaust area. And for the first time, he demonstrated that in kinetics, we see a certain mechanism of separation of particles on pitch angles that leads to the emergence of transverse anisotropy of plasma in the exhaust center and longitudinal anisotropy. Physics of reconnection is particularly important for order space weather, which is an important factor when we study this order space of close proximity. And this work gives us understanding of anisotropy in plasma, that is the source of free energy in kinetic reconnection. The results of numerical experiments for reconnection with cold ions are particularly interesting for MMS satellite system. And as for the testing of work, it is confirmed by the published works, and these works were published in the leading journals indexed in Web of Science and Scopus. So the author also participated in the conferences, international conferences of a top level. These are Russian conferences in 2017, 2019, 2020. And he also participated in the General Assembly of the European Geophysical Society in Vienna. And finalizing, I would say that this thesis by Ivan Zaitsev complies with the requirements of the order as of September the 1st, 2016, number 6821/1 on the procedure of granting academic degrees at St. Petersburg State University. And our candidate for the degree, Mr. Zaitsev, deserves the academic degree of the candidate of sciences in physics and mathematics and specialization solar physics. And Article 11 of the above-mentioned order is not violated. So this work is quite a fascinating one, and I was pleased to read it, to analyze it, not being an expert in this field of geophysics. And I really liked it. And I have no significant corrections, but there were certain faults in the text, but this does not compromise the very good impression that I had. So that's it. Okay, thank you very much. So there's nothing to provide an answer to, therefore let's listen to our next review. Please, Elena Grigorenko, you have the floor. So I won't read my review because I've already submitted it, and certainly the goals were already mentioned, and certainly the entire community of physicists recognize the importance of the issues that were considered by the candidate for the degree, and we can compare this modeling results with observations in this sphere. The results are interesting indeed, and some of the results are novel. And also the candidate for the degree has written a very good work. He provided good simulations, and credibility is not questioned. Therefore, overall, my review is quite positive, though there are certain problems and faults. Maybe they're associated with not quite clear formulations and phrases. And there were certain minor mistakes. Therefore, I'll read out some of my comments. They did not compromise. They do not compromise the overall high quality of work, but certainly I would like the author to take them into account in future. So the first remark, maybe it's connected with misunderstanding of what's written. In sections 2.1 and 3.1, the author states that there is a modeling of the process of anti-parallel reconnection typical for magnetotail. And then, in conclusion to Chapter 3, he writes that the kinetic model of anti-symmetric reconnection was considered. And this reconnection in tail is a symmetric one. In asymmetric reconnection, you should have differences in plasma parameters to both sides from the sheet. So it's rather a very specific situation for the tail. Maybe that's a misprint here, or something quite unclearly formulated, because I didn't find conditions for this antisymmetry in the text. So what kind of antisymmetry was it? That's the first question. As for self-congruence, this question was already mentioned. Then in section 2.4, the author describes the functions of ion distribution received in B point. And you identify the interpenetrating beams that move perpendicular to the current sheet plane. And here you make a reference to Hoshino work. Maybe there's a kind of misunderstanding in the terms, because in PSBL we see accelerated beams, and in Hoshino work they were not considered, but they were rather mentioned. So he mentioned the beams that are going out of the current sheet to plasma. And as for interpenetrating beams, they emerge due to reflection in the Earth. Therefore, there's a kind of maybe misunderstanding with a reference to this work, or an incorrect wording on the nature of these beams. Then, yet another drawback from my point of view is that you don't give a range of very important references to our Soviet theoretical school. And you make references to Spicer, certainly that's great, to the works of Cowley, but in the works of Shabansky in 1970s, all these mechanisms during demagnetization of ions, this mechanism was already considered, it was published in Science Review, and this law was got earlier than Crowley work, and you don't make a reference to that. And in the works of our theoreticians, headed by Leonov, they studied the they also considered the resonance effects, they considered the mechanism of capture. So there were a lot of works published for numerical modeling, certainly. Certainly they were not that good, but still I believe that this it would be nice to make a reference to this work and to compare your results with the results in these works. And unfortunately, you don't give it. However, all these remarks do not compromise the high quality of work. It is quite a good one, and it meets all the qualification requirements, and it complies with all the basic requirements of the order and the procedure of granting academic degrees at St. Petersburg State University. And the qualification of our candidate for the degree is not questioned, and I believe that Mr. Zaitsev deserves the academic degree of the candidate of sciences in physics and mathematics in solar physics, and Article 11 of the above-mentioned order is not violated. So that's it. Thank you. Overall, the thesis is a good one, it's a useful one, and the results can be used both in our institute and in other scientific institutes as well. Thank you. Thank you, please. There were several comments. You can answer. Yes, first of all, I'd like to thank Yelena for the review. And as for terminology, anti-symmetric and symmetric reconnection, indeed, we need to be quite accurate when using these terms, because this term, anti-parallel reconnection or anti-symmetric reconnection, these terms are not fully correct, but basically the term asymmetric is mostly used for reconnection at magnetopause, and we frequently use this term symmetric for night side and asymmetric for day side. And the terms that I use, maybe they are kind of jargonisms. Anti-symmetric and anti-parallel reconnection, they mean that at the initial point the magnetic fields were anti-parallel. But certainly I should pay attention to this terms, yes, because these are different things. Anti-parallel and anti-symmetry. Anti-symmetry deals with plasma, and anti-parallel, yes. But I believe you will agree with me that if different parameters of plasma, if there are different parameters on both sides of plasma, I believe it's more correct to use asymmetric reconnection. Yes, certainly. And for the night side, we are going to use symmetric. There were other comments as well. Yes. Yes. Then as for the issue on the beams, in PSBL and in Hashino works. Yes, I fully agree. There was a misprint in the text because in our model we see that in the center of the current sheet we have penetrating beams, and on the external margin we see single directional beams. So that's my mistake. And as for Shabansky work, certainly the domestic scientists are quoted much less in the West. However, they deserve that. But in English literature that I used, the colonym is a kind of, a universal term. And I got acquainted with the work, and indeed, that's really a fundamental work that you need to study. And I thank you for mentioning it. And as for Büchner and Zelonov, 19 of the year 1986, we make a reference to the work of 1989 because it fully considers this issue. And as for his work with Rabdal, indeed I should have studied it in more detail. I did not consider it before because we considered the distribution of pressure in different areas of magnetic tail, different types of anisotropy. That's an important result. However, we consider this reconnection and local distribution of anisotropy, and we consider the configuration which is a bit different for our reconnection process. And that's it, yes. So have you finished? Yes. Okay, now I would like to give the floor to our next speaker, please, Eldar Shahislamov. You have the floor. Well, the topic is quite relevant, sure enough. And I believe we'll have a lot of defenses dedicated to the topic, because there are certain events in nature that are considered quite deep. And one generation of physicists did not manage to resolve these problems. And if we go more specifically, this work is based on the application of methods of kinetic modeling. That certainly is the most adequate choice for such tasks. And the author demonstrated that he mastered this instrument in order to resolve different goals in different conditions. And in this work, he studied several important aspects connected with separatrices and the outflow zone. Separatrices are still the most complicated object or place in the process, and we still need to continue to study them because the major acceleration happens there, and certainly they are of particular value. There are three results that the candidate for the degree got. So basically, I won't repeat all these results because we've already heard them. And as for the drawbacks or questions that remained, the standard issue in such studies is the influence of results on the mass of protons in the model. maybe the candidate for the degree will tell us about the most recent advances in this topic. And I would also like to mention that it's clear that there are a lot of works on modeling across the world, as far as I'm concerned, on numerical modeling of reconnection, especially in 2D geometry, and certainly there must be works that deal with the same topic, and unfortunately in the thesis you don't provide the results of other scientists on the topic, in the topics that are quite close to the one that you've chosen. So you have an impression that that's something really novel and unique, that no one really worked on that. Though I'm sure that it's not the case, because there are a lot of works on the topic. And I would like to mention that, as for comments, that you don't substantiate the conclusion on the speed of acceleration, and you don't have enough of these intermediate points of temperature. So that's what I wanted to mention, how important it is for the conclusion. But overall, the thesis is quite interesting, and as it is the candidate for candidate for the candidate's thesis, it meets all the requirements. Therefore, I believe the thesis titled Acceleration Mechanisms of Thermal Ions During Magnetic Reconnection meets the requirements of the order as of September 1st, 2016 on the procedure of granting academic degrees at St. Petersburg State University. And I believe that Mr. Zaitsev deserves the academic degree of the candidate of Sciences in Physics and Mathematics in Specialization 010303, Solar Physics. And Article 11 of the above-mentioned order is not violated. So that's basically it. Okay, thank you. Please, you can answer the question. Okay, I would like to thank, first of all, for the review. And as for the first question on the relation of mass of electrons and ions, and how can it influence their and how their change can influence the results. It's important that in Lepenta work it was demonstrated that with approximation of a relation of masses to a real sheet on separatrices, the layer becomes thinner. Therefore, we can say that separatrices acceleration should be more efficient. As for the comparison with other numerical experiments, in numerical modeling of magnetic reconnection, there were a lot of works dedicated to the topic, and certainly you can't mention all of them. However, I should have given a more broad review. But as for the modeling with cold ions, I give a reference to the work of Dargent of 2017 that considered the structure of the reconnection sheet with cold ions on daily magnetopause. Whereas we hold experiments with cold ions in magnetotail for the first time. Therefore, the substantiation of conclusion on the growth of so there was another question on the substantiation of the conclusion on the growth of speed of reconnection in cold simulation. This is an issue for the future, but colleagues from Chinese group outpaced us. They did several simulations using this code, and a month ago they published an article in which they confirmed this dependency quite obviously. organizing 4 numerical experiments, not 2, but 4. So, dear colleagues, we have certain problems with our connection with Mr. Troyan, so I have to announce the first technical break. Oh, here he is, and we'll lose connection. So do we announce the technical break? Vladimir, is everything okay? Vladimir, we lost you. Yes, everything is okay. Everything is okay. All right, there's no need for the technical break then. Okay, now we move forward. So you've answered all the questions, and now we can shift to our next review of Andrei Samsonov. So please, Andrei, you have the floor. Yes, thank you. Basically, as for the relevance of the study, we already mentioned that. Indeed, magnetic reconnection is a universal process that exists in magnetosphere and in solar matter and on the solar surface and in faraway galaxies, as they believe. And today, we see the active studies of magnetic reconnection on macro scale, thanks to kinetic modeling, thanks to state-of-the-art space machines like MMS. And kinetic modeling is quite actively developing because we see the development of computational capacity, the increase. These capacities increase and we can launch more particles, and thus we can discover something new in the field. And Mr. Zaitsev did a lot of work. He studied the numerical code of IPIC 3D. He mastered the supercomputer of the Moscow University. That's also quite complicated, this work on a remote computer. He managed to sort out and interpret the results that he got in modeling. So this work was quite significant, and he received many interesting results. And as I marked in my review, the most interesting was the comparison of the magnetic reconnection in case of hot and cold ions. So he studied everything in detail, the acceleration of particles in one or another case, what kind of difference is there. And he also demonstrated that the reconnection speed is high in cold ions. And these results are also important and quite relevant. Because I know that it's quite actively discussed today that cold ions from ionosphere can penetrate the tail in this area of magnetic reconnection, and they can influence this process of magnetic reconnection. There is a rise of energy there, and then they move forward to traditional bands, to auroral band, and so on. So basically that's it, and it complies with the observations. And in my review, I've given certain comments. And the first thing that I wanted to mention is that there's kind of lack of discussion of numerical model that was used. Certainly, I understand that this numerical model was not developed by the author. The author used a ready-made numerical model. That's quite okay, because the majority of scientists are using someone else's models. And I'm sure that there's a range of publications on the model. Maybe you should have described it in detail, the results that this model got, the testing that it had. And I had two theses on numerical modeling, my candidate's thesis and doctoral thesis, and colleagues will support that that I've had separate chapter dedicated to the testing of the model that I devised. And taking the advice of my colleagues, I carried out a range of tests and demonstrated that the model corresponds with the requirements. Maybe in this case there was no need to introduce certain additional tests, but I believe you should have described this model more, the testing of the model and the use of it. And regardless of certain minor comments, overall the work is quite a good one. And I believe that it deserves. And as colleagues read this part, I'll read it out as well. So the thesis by Mr. Zaitsev meets the requirements of the orders of September the 1st, 2016 on the procedure of granting academic degrees at St. Petersburg State University. And Mr. Zaitsev deserves the academic degree of the candidate of sciences in physics and mathematics and specialization 010303, solar physics. And Article 11 of the above-mentioned order is not violated. That's it. Thank you. Thank you. The answer, please. Yes, thank you so much for the review, and I'll shortly answer about the marginal conditions and about the description of the numerical code. This code uses the scheme with some implicit moments that allows us to eliminate the limitations for temporal step that we have in current conditions. And we also use periodical marginal conditions that allow us to avoid marginal effects. But still there are new limitations introduced for the time of simulation and by the size of our computational area. And indeed, this code IPIC 3D was tested several times, and a lot of results were achieved due to it, but this code was not the main topic of my study, therefore I applied it to achieve a specific goal. Okay, thank you. And the final review, it's mine. I'll try to mention some basic points. First of all, the relevance, the credibility, and so on. It was already mentioned, but I'll give you some ideas as well. First of all, this work is based on numerical modeling, and it studies physical mechanisms of acceleration of ions in the process of magnetic reconnection. The relevance, as it was already mentioned, is associated with the fact that the reconnection process is a fundamental one. Explosion type process in outer space plasma, and it can be applied in many spheres, and in particular in Earth magnetosphere, it controls a pace of supply of to magnetosphere. It also covers the explosive events in the tail that creates magnetic storms, and these processes influence the functioning of important satellite systems. And it was also mentioned that physics of reconnection is in the focus of our international community, and today we see an international MMS project dealing with the topic. And as for ion characteristics, the thing is that this topic was not given a lot of attention recently due to the fact that ion parameters, cold ion parameters in magnetic tail were measured poorly, and they started to measure them in the most recent decades, and it turns out that their parameters, the parameters of the plasma, are quite varied. Therefore, there is a question how it will influence the pace of reconnection and consequences of reconnection. Therefore, this aspect, private aspect, is quite a relevant one as well. As for novelty, there are 3 results on the pace of reconnection in changing the temperature of background plasma. That's a rather valuable result. There certainly you should have taken more points, but still, as you mentioned, Chinese colleagues have already given this result. Okay, so everything is okay here. So they confirm these results. Okay, that's great. And second point, the description of acceleration of ions at separate traces and the generation of anisotropy depending on different parameters. And third point is the acceleration of ions in a current sheet that leads to longitudinal anisotropy. So these results are quite novel. And as for credibility, talking about that, we should mention 3 points. First of all, the accuracy of supercomputer calculations that is supported by the results of modeling for hot plasma that were previously received by other authors. So you can compare the figures, the images, so we can see that code application was tested. Second, the results of detailed calculations are quite volumetric, and for each point there's a lot of there are a lot of numbers that you need to process. Certainly that's quite a complicated task. And these results in separate points were confirmed by analysis of trajectory calculations in simple models that allowed to study their parametric dependencies and so on. The results, as I've already mentioned, are well represented, and I would add that in March, in Physics and Plasma Journal, an article was published, and Ivan is the main author there, and it has very good representation of the results of Chapter 3. Unfortunately, it was not published here, but quite formally we should not take that into account. But I believe this this demonstrates the recognition. And as for value, practical value, I can mention 2 points here. First of all, this work gives important information on the dependency of intensity and the process of reconnection on ion component and on ion exhaust. And I would mention that it seems to me that the major mass of ions, this exhaust, penetrates through separatrix because it's quite large in the tail. And it means that the mass load of this exhaust is defined by this process. And if we recall the major consequences of reconnection process, first of all, coronal outburst of mass. And this mass outburst and the movement, the effects of interaction with background plasma, so they are defined here, and that's quite an important aspect that was covered here in this work. And also, I'll skip the description of work. And in chapter 2, I would like to mention that these materials are of methodological importance. You know, this description of reconnection is quite a hard task. The dependencies are non-trivial and they depend on the point taken. So it's quite hard to introduce this topic to students and to make an overview of this topic. So in this case, I would like to mention that in chapter 2, the author took the results of one simulation and using it, he demonstrated different structures, types, interdependencies, and that's quite a useful demonstration that can be used in courses in which we try to get our listeners acquainted with this interesting process. So I had a remark in chapter 4. You consider acceleration of thermalization of ions on distances from X line. As an analogy, you study the kinetic problem according to Harris that was considered previously an approximation. And as far as I'm concerned, this is quite a vague description and there's no separate part in which you describe it in detail. For example, the description starts with a point of 174 reverse higher frequencies. What happened before? What happens afterwards? So that's a mystery. And is this moment characteristic or not? So you don't provide description for that. And overall, if we assess the work, it considers relevant issues of magnetic reconnection that deal with the behavior of ion component of plasma, and the 3 provisions brought for the defense are new results, and they are important in order to understand the formation of laser jets and their mass. And these results will be quite in demand for interpretation in a mass project, and colleagues mentioned that already. And overall, that's a very good work. It has certain drawbacks. And maybe they are associated with the fact that, judging by the submission date, the candidate tried to finish this work on the day of on the year of graduation from PhD course. And that's really good, and we can't blame him for this desire, but maybe this did not allow our candidate for the degree to check everything. Therefore, there are a lot of insignificant failures and drawbacks in the work. But basically, there are certain misprints and inadequate wordings. I won't give you the list of them. And there are certain vague formulas. For example, on page 49, he described this constant equation, and it should be equal 0. It should equal 0. So certainly it means that you've read it, but you just missed these points. And there are certain uncertainties, and sometimes you even drop explanations that would be quite useful for the readers. And that's for the first comment: misprints and poor wording. Second comment: you don't provide the substantiation of the choice of numerical values of model fields. You take the model field, you calculate the trajectory of many particles. And the values that you've taken, they should be quite characteristic, and you need to substantiate them. You don't give the references to experimental values. Why Hall electric field is taken as 1. What is this range that it can be applied to? And in order to substantiate the choice, I believe you should have given these references because it's important for the reader to understand how general these results are and how representative they are. Third comment is dealing with jargonism, and this was already mentioned. This jargonism has a lot of abbreviations, and between ourselves that's possible, but in public work you should minimize them or you should describe them, explain them. For example, you write, you don't define these definitions. Anti-parallel reconnection. Reconnection of what? What's anti-parallel here? You can consider it as a kind of abbreviation, but first of all you should introduce it. So maybe you did it somewhere in the beginning. Then, Alvin, exhaust, Larmor electric field. What does it mean, Larmor electric field? There's no such value in physics. Or convective electric field minus V multiplied by B. So it's clear where you take it, but you need to define it, to give a word for that. That's not an electric field. Electric field is something that you can place to a Maxwell equation, and it meets the needs for this equation, and this value does not do that. And certainly this work would be better if you would conclude it with a short summary of applications, and if you would provide the specific forecasts of the theoretical model that can be checked in the satellite experiment. Certainly this would be great, but this does not compromise the overall high value of this work. And overall, I believe that our PhD student is quite a well-prepared researcher. He mastered a very complicated issue, and he studied high-tech method of supercomputer kinetic modeling. And right now, in conclusion, I would like to read the following words. This is by von Zaitsev, titled Acceleration Mechanisms of Thermal Ions During Magnetic Reconnection, meets the requirements of the orders of September the 1st, 2016 on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Zaitsev deserves the academic degree of the candidate of sciences in physics and mathematics and specialization in solar physics, and Article 11 of the above-mentioned order is not violated. And that's it. That's it. Thank you. So please, there were comments. You can answer them. Okay. Thank you very much, Professor, for these remarks. Certainly, what you mentioned is quite relevant, and I need to correct this formula. Certainly, I agree with the remarks. As for Hall of field values in test simulations, we should mention that this choice is explained, for example, it is explained by what we see in this peak of 2D simulations, and if we shift to renormed values that are observed on satellites, we'll have just the same correlation, BZ equals 4, and that's half of the field of the reconnected component, and whole electric field is roughly 1. So that's a localized field, and it's larger than a reconnection field, certainly. And I would also like to say that indeed the literature sources list can be expanded. It requires more links to observation works. And as for jargonism, once again, I would like to explain that anti-parallel reconnection is a case of reconnection in which the initial stage is defined by current sheet with a strictly anti-parallel magnetic field without the leading magnetic field. Alvin exhaust. That's a translation of this term exhaust introduced by Gosling, and it is quite widespread. in literature. Well, why it's Alvin? Because it moves with a speed. Yes, but you should have mentioned that in your work. If that's an abbreviation, you should define it. Okay. And Larmor electric field is the term that was introduced by Malaket on the work of 2013. That's an electric field that we see in the proximity of a X point during the asymmetric reconnection at magnetopoles. That's a really local term. Certainly I should avoid this later on. Okay. So I used it because this electric field is something that we see as a result of the effect of this anti-Larmor radius. And as for the application, the most interesting application would be to check this the velocity change with a drop of temperature of ions in this experiment of Harbin Technological Institute, an experiment that modulates magnetosphere. But as for the application of simulation results to observations on current satellite missions, that's one of the possible scenarios of the development of this work. Maybe we'll continue looking for these beams accelerated on separatrices, so I should have a more in-depth analysis of the component of the distribution function on separatrices. Okay, thank you. Now, dear colleagues who are not members of the board but are still here, you have an opportunity to give your review, if anyone is willing to. And I would like to ask whether we had any external questions submitted. None. Okay. Okay, no questions. So a lot was already mentioned, a lot of speeches, a lot of reviews, and we've considered different aspects in detail. So now we should give the floor to the thesis supervisor. Please, Andrei, you have the floor. Well, as a thesis supervisor, I would like to give certain comments. First of all, I'm really glad that we managed to organize this defense in this semi-real regime, and that we managed to provide the results of this long-term work. As the thesis supervisor, I've been working with Ivan for a very long period of time, since his master's course, and I can say that the basic characteristic of Ivan is the opportunity to revise a lot of, to process a lot of experiments and give a valuable result. And he demonstrated it quite well during the defense. And during his master's course, he was fascinated by computation and the method of particle in the cell. And one-dimensional method, he studied the development of reconnection. He studied the formation of blast waves, and he continued this work in the PhD, during the PhD course, and this led us to the study of parallel anisotropy during the reconnection process. Then during his PhD course, he shifted to 2D process, so he made a step forward, and certainly this the main goal was this configuration with cold ions. And as Ivan emphasized, this configuration is possible in the magnetic tail when you see cold ions in magnetic tail in this reconnection area, and they get there from Earth's ionosphere. And before we performed these simulations, there was the dominant point of view that cold ions, as they have a small gyro radius, they are frozen in the magnetic field, and nothing happens with them. So the observers believed this fact that cold ions are frozen in, nothing happens with them, there's no acceleration, and basically there's nothing to model here. When we modeled it, it turned out that there are these accelerated perpendicular beams, so everything that was mentioned by Ivan. And Ivan demonstrated that there is this area of perpendiculars, anisotropy on separate traces, and basically we didn't have such results before, regardless of this 20 years of modeling of this problem using this method of particle in the cell. So these were novel results. And what else? Above all, the thesis has not all the results that Ivan received. For example, he studied the issue of these instabilities in such configurations, and these instabilities are associated with the fact that in cold ions we see a lot of ion beams, and we can have ion sound modes or hybrid electron modes. So this was the topic to which his Vienna report was dedicated to, and he also has delivered his reports on conferences in Apatiti and on J Cosmos conference, and he continues to help me with students, and this requires a lot of time, certainly. And what else? And this chapter of his thesis was published in Physics of Plasma, and a month before our work, Chinese issued similar simulations, but they had slightly different goals of study. And this month, an American group also published a study of the dependency of the speed of reconnection on the temperature of inflowing plasma. They confirmed that this coefficient of 1.5 or 2 is really present in case of simulation with cold ions. Thus, the results that Ivan got were confirmed quite recently, because this problem was quite a novel one. So that's basically it. That's my review. And I believe that the thesis is a really good one. And certainly Ivan deserves the academic degree of the candidate of sciences in physics and mathematics. And the thesis is a good contribution to the study of magnetic reconnection physics. Okay, thank you. We'll listen to our thesis supervisor, and there are some procedural points. I need to ask the members of the board if we have any questions left associated with working in the remote mode. I'm not quite sure about why there's a need for such a question, but if there are any questions, please feel free to ask. Okay, then let's move forward. Does anyone else want to speak out? No questions were submitted online. Okay. So we stop this taking of questions. So the comment was, I would like to add a comment. I didn't see the face of our candidate for the degree, so if I meet him somewhere, I won't recognize him. So please come up to, yes, let's zoom in. And we'll get you acquainted with our candidate for the degree. Okay, yes, we see him. So it's 3 It's 3:45. Now we shift to the vote. I have a question to the members of the board. We have an opportunity to discuss everything in closed regime, in the closed mode. Do we need such an option or not? No, no need for that. Okay. Okay, we are going to discuss everything straight away. Okay. Now let's shift to the vote, and I raise the question on the award of the academic degree of candidate of sciences in physics and mathematics in academic specialization, solar physics, to Ivan Zaitsev. And let me remind you that the decision of the Dissertation Board on conferring the academic degree is positive, provided more than 50% of the board members, but not fewer than 3 people, voted in favor. So let's start. Professor Zolotova, what's your point of view? Certainly, I believe that Ivan deserves the academic degree of the candidate of sciences in physics and mathematics. Okay. Vladimir Troyanov, yes? I also support this point of view. I believe that that's a good work, and certainly Ivan deserves the academic degree of the candidate of sciences in physics and mathematics. And I wish him further success. Thank you. Elena Grigorenko, what's your opinion? I also support the award of the academic degree, certainly. Okay. Professor Shahislamov, what about you? I also support the award of the academic degree. And Andrei Samsonov, I also support the award of the academic degree, and I believe that Ivan deserves this degree. Okay. And I also believe that that's a very good work, and Ivan deserves this academic degree in specialization solar physics. Thus, distinguished colleagues and guests, I would like to mention that out of the 6 members of the board, 6 voted for the award of the academic degree, no one voted against, and no one abstained from the vote. Therefore, we decided to award the academic degree of the candidate of sciences in physics and mathematics in specialization 010303 solar physics to Mr. Zaitsev. So, distinguished colleagues, due to the fact that our session is held in this hybrid mode, I would like to ask the members of the board or the candidate or Mr. Zaitsev or anyone else present, I would like to ask you if you have any comments on the procedure. No comments, and I believe we should thank the chairman for the wonderful for his wonderful work. Okay, thank you. And now we can give the floor to Mr. Zaitsev for finalizing remarks. Yes, thank you so much. First of all, I would like to thank those who made this defense possible. I would like to thank the organizers, the members of the Dissertation Board support, and then I would like to thank my parents. I hope that they are watching the broadcast. And I would like to thank my friends from the university whom I worked with together, whom we worked with together. And I would also like to thank all my teachers and all my professors for sharing their knowledge with us. And certainly I would like to thank my department for this fascinating academic life. Indeed, that's true, and that's a priceless experience. And I would like to thank our lab of the physics of magnetosphere, and I would like to thank everyone present. And I would like to extend separate gratitude to Igor and Valerievich and Marina Valerievna for adding up some positive points to our sessions. And I would like to thank Viktor Andreevich. Thank you so much for the courses that you've given, and thank you very much for the work that you do. Thank you very much for supporting the work of our department, and certainly getting this degree was possible due to my thesis supervisor and my consultant. Thank you very much for these hours of discussions, for these days of discussions, and certainly the person without whom this dissertation would never become real. It's hard to express my gratitude to my thesis supervisor, certainly. Yes, thank you so much for that. So that's basically it, and we congratulate Mr. Zaitsev with a successful defense. And I therefore close our session. Thank you everyone for participation, and kindly turn off the broadcast.